Okay, question 3. Again, using the same model system, but the idea is to get that amine group on the right side attached, we have to make um, a variation of a hemiacetal or variation of an acetal called hemiaminal ether. The idea is we're essentially doing acetal type chemistry, but using a nitrogen as one of our nucleophiles instead of another oxygen. So it's not any different. It's basically the same mechanism. So a few things. One, this is a retrosynthetic arrow. This means that reality goes the other way. It means this is the final product made from these two. Two, when I put something in bold and capital letters in a question, it generally means I'm trying to help you. If you're trying to draw this using the full structures, inexperience suggests you're more likely to make a mistake. Not because you don't understand the material, but because it's a little complex. When I say use simplified model structures, I mean use those. There's not so many extra atoms around. You're not worried about the ring and which nitrogen is the useful one. You're not worried about which of these other alcohols could do anything. Reality is they don't, but we're not in that point yet. We haven't done carbohydrates yet for you to know that. So I wanted to make this as direct as possible and keep it on topic. So I gave you simplified model structures. Some of you thoroughly ignored that and made your lives more difficult. Please don't do that. I'm trying to help. I know the material's difficult. I'm trying to make this at least slightly more direct. All right, so let's have a look how we're going to get from A to B here. This is a relatively direct mechanism. Again, it's just like the last half of an acetal formation. It's exactly the same. So what we're starting out with is we're starting out with this and our amine group, two methyls, a lone pair, and we have acid. So what we're doing first, we need a leaving group. That has to be it because it's not there in the final product. So here we go. We protonate first. Anytime you have strong acid present, that generally is the start of the process. Then that's going to get displaced internally. Now, some of you displace this directly. Very unlikely. Not impossible, but very unlikely. That is a secondary carbon and one with fair amount of bulk around it. It's unlikely you're going to be doing a straight SN2 type displacement of that with the amine. This is much more likely that you get rid of it and temporarily form an analog to a carbonyl group, which is the basis of, I don't know, the chapter that we're talking about. So then we can attack that directly because we could draw a resonance structure for that and have a positive charge directly on that carbon. So at that point, our nitrogen is already attached. We're basically already here. We have a protonated nitrogen and everything else is where it's supposed to be. So we just need something to take care of that. Could be an extra molecule of the amine, could be water, doesn't really matter which I use here. But the idea is we're going to neutralize that and we're done. We now have our connection of the nitrogen to the ring. And it is basically the same as an acetal. Remember, an acetal would be this. So I could even draw an acetal for the ring itself if I wanted to. If I had done this with an alcohol instead, done this with methanol instead, for instance, instead of the amine. I don't know why the pen doesn't work in this area, but if I'd done it with methanol instead of the amine, I would have gotten here. So this is a very similar analog to an acetal. Same chemistry, same mechanism, basically. A little bit better of a nucleophile with the amine, but a little bit more basic, so a little bit different condition-wise. The other part about that question I had to point out, and I want to say it again just for clarity, is that we're looking at simple examples. The way this is done biochemically involves quite a few tricks that we can't do. or that we don't use chemically. Biochemically, you're limited by not having extreme pHs. You can't run sulfuric acid through your veins and survive. Not having extreme temperatures. You can't go boiling your water in your veins. That wouldn't do well with your cells. So there are some serious limits, and therefore biological systems have evolved ways around them. We don't use those. We just hit it with a sledgehammer because we're not worried about breaking cells or killing living things in chemistry. We can make it harsh conditions because they're faster. But never assume when we talk about biological examples that biologically it's made exactly the same way. It's generally a lot more complex because of limited temperature, limited pH, limited solvents. Again, you can't even run a good solvent through your body. You've got water, that's it, the end. So, there are a lot of limitations to chemistry occurring in a biosynthesis that we don't have as chemists. So when we use a biochemical model structure, the way that we make that is probably very different than the way that a cell would make the same thing.